Get ready, you know?
Do some pretty similar training.
Oh, yeah. Like my surf stretches, yeah.
Okay. So we're very happy to have Professor Douglas Jerolmack from University of Pennsylvania to be here to give us a talk about his recent research on the landscapes of glass. I won't spend too much time on introducing Doug. I think you will learn him more from his talk content. That is also the way Doug prefers. And let's leave the time to Doug. Let's welcome Doug for his seminar.
This is the first time that I actually am able to give a talk while watching the wave. So if I'm like looking off in the distance with a steely gaze, I'll try to make it look like it's deeply intellectual, but it's probably just that I'm seeing if it's peeking up a little more. Anyway, thank you all immensely for having me here. I know people say this, but I'm having a great time. And if it doesn't become clear in the talk, I'll say it now. One reason I'm super excited to be here is to visit Vishal in his lab. So I got to see the lab for the first time. And some of the themes that I'm going to talk about will maybe be complementary, but resonate with some of that work. And I'm also on sabbatical at UC Santa Barbara. So this time, actually, I'm just up the road a little bit. If for some reason you happen to get interested in anything that I'm talking about or want to know more about it, just reach out to me. And if you just tell me that you were here and you got a question, then we can talk. One reason that I give talks is so that I can get more ideas of what to do next. Okay. So unfortunately, that little thing there looks like it's gonna block the top slides, but that's fine. This is a landscape of glass. Okay. What'd you say? You said I can move that thing, or how do I do that?
You can hide it.
Oh, how do I hide this?
If you go with more on the right,
Yes.
you could hide.
Hide video panel.
There's another hide.
I can just like do that or something. Okay. Oh, that's as high. That's all the way to the top. That's not what it'll let me do. Anyway, that's fine. That's fine. We're all good, right? All right. Yay. So this is a landscape made of glass. These are actually glass panes here. They're thin, so they're quasi 2D, just arranged in such a way so they look like a set of mountains. This is modeled after the Blue Ridge Mountains in Virginia. And first of all, I think this is beautiful. Anybody looking to get me a Christmas present or something, I wouldn't mind if you went to Stone Ridge class. But the other thing is that what I want to try to convince you of today is that this picture is not only an apt metaphor, but that in a lot of ways, landscapes that we see, essentially the surface of the earth, is literally a glass. And as long as you expand your definition of glass to not mean literally in amorphous solid at the molecular level, but rather solids that are amorphous, where you replace molecules with essentially any particle, whatever the particle happens to be, colloidal, granular, etc. And I want to convince you that making the connection that landscapes are glass has some important implications for the way that we think about the mechanical deformation of that material and ultimately how that material fails. So my former PhD student, Nicole, likes to put this into his talks, and he inspired me. This is Randall Monroe of XKCD fame. And there's a nice little New York Times article with illustrations by Randall and quotes by Karen Daniels, who's a colleague of ours. And it's a question about, the question from a reader was, what makes sand soft? But the illustration that got a lot of fame is this one right here, right? Because it turns out that the answer of what makes sand soft is pretty hard, right? And so in the area of physics by difficulty, right, you have increasing levels of difficulty with a pile of sand being at the end. This sounds like a stretch. It is not. A lot of interest in the physics of materials is on phase transitions. And if you think about sand, for example, it can behave as a solid or a liquid or a gas, and the transitions between them are not the normal thermodynamic kind, where molecular fluctuations are relevant. You actually have more like structural disorder and stress that becomes relevant, right? And so the pile of sand itself might look pretty innocuous. The first thing that I want to show you is that even a pile of sand sitting on a table here is not an innocuous pile doing nothing. Now that in itself is an entire world worthy of study, and that there's some surprising things that happen, right? So I work at an institution where all of earth and environmental science is in one department with 9 faculty. This is an absolutely massive institution with a huge amount of geophysicists that I'm very jealous of. But you could argue, I'm not saying everything falls along neatly, but that if we think about geophysics, so we know there's a long lineage of solid earth geophysics, which starts with certain assumptions about the material properties that we're interested in, and then works to understand them. And then there's a whole other long lineage, of course, of geophysical fluid dynamics. And I guess my first question is, where does a pile of sand fit in here? And I mean that literally. I mean, if we want to understand and study the behavior of the granular material that makes up and covers the surface of the earth, where does it go here? Where does it go in terms of the lineage of research that we can draw on? And literally, where do we do it? What I mean to say is, where do you work? Who do you talk to, right? Which textbook do you look at? And it turns out that there's some, those textbooks are changing. So I just, first of all, ask the question about, what does a soft earth geophysics look like? We know the hard parts of the earth. It's not all solved, but we know a bunch about it. We know the fluid parts of the earth. What about the parts that are soft? The parts that are solid under some excitations and are liquid under other excitations, and that vacillate between them under even gentle forcing. A little bit of rain and solid soil becomes liquid, a little bit of shaking, right? These are obviously problems that have been studied. But what I want to do is focus on the nature of the transition between solid and liquid itself, and try to argue that we need some new tools and perspectives. So I work on a lot of problems that are related to particles in a fluid out there in the environment, right? So I'm not going to talk about all of those things, right? But from wind-blown sand dunes to turbidity currents in the deep ocean, I haven't done much with pyroclastic density currents, but I'm interested in debris flows and other things. But stepping back, we can think about the range of particle fluid flows out in the environment, and we could define them maybe, or at least place them in a parameter space, a 2-parameter space, where the y-axis is solid volume fraction. This is the concentration of particles. So solid volume fraction, 60% means concentration of particles is 60%, and I'm agnostic to what the balance is. It could be air, it could be water, it could be something else, right? So we're just asking how much of a volume of particles and fluid is filled up by the particles themselves. On this axis, I have it plotted as dimensionless shear rate, which I'm going to get into later in the talk. But for now, you can think of it essentially as an inverse viscosity, okay? So as I move along this axis, I have increasingly fluid-like behavior and correspondingly decreasing concentration of particles. So up here is where dry soil sits, right? And dry soil is sitting here. It has a high solid volume fraction. It creeps very slowly. And if we shear it just a little bit, typically this material will dilate. So there's a slight change in volume fraction and you can trigger a landslide. You mix some more water in with it, the contacts between the grains can become lubricated, and you can have things like debris flows, and you can keep on marching down here with increasing degrees of adding fluid, increasing contributions from turbulence. There is a little thing hanging out down here, by the way, which is mud. If sand occupies a special category of hard, mud occupies rarefied territory in the phase space. In this phase space, mud is sitting over here. Mud can exist at a very low volume fraction, so it's mostly water with a little bit of particles, and you would think that it should be not solid-like. and yet exhibits elastic-like behavior. So, you know, mud can basically act like hair gel, right? You put a dollop of hair gel on your finger and you push on it a little bit and it can elastically deform, but if you push on it too much, it flows, right? And so same here with these fluid muds. I'm not going to talk about them today, but we're working on them. If you're interested in this category over here, just ask me, right? And so these are granular fluid mixtures behaving as a solid, as a liquid, or as a gas. And by the way, when I say that, I mean it literally, right? This has whatever modulus you want to measure for solids, this has it. Granular flows in the liquid state can be described by the shallow water equations. Dilute granular gases can literally be studied or modeled with kinetic theory that we use for ideal gases, with a few changes of variables, obviously, to account for the fact that it's dissipative. And so what's the nature of the transition? The nature of the transition between the solid liquid state and the liquid and the gas state. This liquid to gas state is a really gradual, continuous transition. Where you draw the line is actually hard. Everyone can agree about what the dilute state of these flows is, where the grains are not interacting frictionally at all. Everybody can agree what a really dense granular flow looks like, and it can be well modeled with the shallow water equations, but this is a very gradual transition. This transition right here, right, between the solid, apparently solid, and the liquid state of grains can be rather abrupt, right? So think about liquefaction of soil, something like that. A slow moving earth flow in the creeping state, and then it rains a little bit and it suddenly liquefies, right? So this transition can be rather rapid, and that's one that we're going to focus on. So I asked the question, what does failure look like? So this is a famous landslide in Big Sur. You're looking at a map of velocity or deformation rate of the surface. Okay, and this is in Northern California. This is California Highway 1. This is a paper from Al Hanwerger and colleagues, and they were using differential INSAR data to basically look at the deformation that was happening on this landscape leading up to a catastrophic landslide. So I'll play the movie again, and what you're looking at in this movie, this is all deformation. You see the velocity in meters per year before a catastrophic failure, right? So it's raining a little bit on this hillside, and you can see that there's localized regions where the flow is speeding up. You see these regions popping off here and there, and then eventually these regions grow and they coalesce. And when the high displacement regions coalesce across the entire mountain face is the point of failure, right? This is actually very typical of what failure looks like in disordered or amorphous solids, okay? So I'm just going to give a little brief overview. If you don't know this stuff, and if you do know this stuff, don't be insulted by how simply I'm going to talk about it. But the most common amorphous solids that have been studied for a long time now are glasses, right? And I mean like molecular glasses. And the way to think about a glass is it has the disordered state of a liquid that is quenched into the solid state, right? So the molecules are organized in a haphazard fashion, and there's no minimum energy configuration that's going to make them all happy, right? And if you have a glass, we can't see the molecules in a real glass, but we can do simulations, right? So this now classic paper by Falk and Langer, they were interested in how glasses yield under shear. And so they have this, molecular dynamics simulation of a metallic glass where they apply strain at the boundaries. And the question is, how does that strain get accommodated in the sample, right? So I force it to deform at the boundary. And if this was a liquid, of course, you would have like a linear strain rate profile if it was viscous, right? And instead, in this disordered material, what you see is that the strain is accommodated locally in what they called shear transformation zones. One way to think about this, these are liquid inclusions, okay? You're shearing the glass, and what literally happens is that locally regions become above yield and they fluidize temporarily. And so you have these little fluidized regions. If you strain it more or you strain it faster, what happens is that you get increasing number of fluidized regimes. And when the fluidized regimes all link up and percolate a network across the sample, you get global failure. So they recognized that the way in which we hit failure in a glass is that we fluidize locally and then we link up the fluidization, right? So there's the yield problem, by the way, starts to get connected to problems of percolation, which has a long, rich history, right? And that might be analytical solutions, but not yet. Remarkably, Dave Waits' group came along and said, well, look, we'd like to do some experimental confirmation of this, but we can't do experiments where we can see what molecules are doing. But realized that you could take a suspension of colloids, so they're particles in a liquid, and they're small enough to still undergo thermal agitation, Brownian motion, like molecules do, but they're big enough that you can see them in a microscope. So they took this as a model glass system, straight at the boundaries, and sure enough, they saw that there were these localized shear transformation zones, and that as they increased the strain, that they linked up. Doug Durian and other of my colleagues in physics at the University of Pennsylvania found similar things in driven granular systems. And the basic idea is that we know that structural defects, if we're talking about subcritical deformation and creep in solids, that is always related to structural defects. But in a crystalline material, you say, okay, it's a defect game. So I'm going to look at the defects and I'm going to see how the defects migrate. In a disordered material, it's essentially all defects. And the defects interact with each other, which means that you can't take an additive model of defects like we do for crystalline materials. You need to take a different view, right? And so, but ultimately for us, it's to understand that in this disordered arrangement of particles, be they atomic, colloidal, or granular, that you essentially have soft spots, localized regions of dislocation and flow. And it turns out that there are some common properties at which associated with failure of amorphous solids, whether they're molecular, colloidal, or granular. For example, in this paper with a whole bunch of authors of us at Penn, we showed that all of these different materials that you see here will fail at 3% strain. Why 3%? Nobody knows. But glasses, colloids, granular materials, if you strain them up to 3%, they will globally yield. So why is creep in amorphous solids so difficult to understand? So this is another illustration. Lots of people have been doing this technique of visualizing how forces are transmitted in granular materials. But the work that I like the most, and the person who's used this stuff to great effect is Karen Daniels, our colleague. And basically what you're looking at right now, so these are discs, okay? They're two-dimensional discs and they're soft. So they're little discs that are squishy. And what you do is you shine light through them. You have a polarizer and a cross polarizer, and you see the light on the other end. What happens is when these discs get squeezed, it actually changes the refractive index of the disc. And when it changes the refractive index of the disc, it gives this interference pattern that you see here, this birefringence. And what that means effectively for us is that when things are squeezed a lot, they light up more, right? And so what you can do then is that when you squeeze a granular material, what you see is that the stress is not transmitted uniformly through the material, but rather the stress is focused along these networks of particles that happen to be in more rigid configurations. And that most of the particles, or at least many of the particles, are not participating in transmitting that stress at all, right? So in this experiment down here, what's going on is that this is a disk with particles that are glued to it that is rotating, and inside of it is a granular pack. And you can see, so you're shearing it at the boundary, and all of these colors lighting up are where the forces are strong. So this is a subcritical deformation forced on a granular system. And you can see how the stresses get transmitted non-locally, concentrated over great distances. So stress transmission occurs through enduring force chains. And this is one of the things that makes creep so difficult to understand in these materials. Now, there are some similarities in how creep occurs from thermal to athermal systems. And I had mentioned that before, but I want to get a little more specific about it because it'll set us up for the first experiments from my group that I'm going to talk about. So there was this neat set of experiments that was done by Olivier Foulican's group. They were interested in how thermally driven creep would relax a granular pile. So what they did was they put a bunch of grains in a drum. And this is kind of a typical thing for granular flows. You put it in a drum and you rotate the drum. However, in this case, the drum is tiny, tiny, tiny. So they're putting in particles that are about 1 micron size immersed in a bath of liquid. And they put them in a drum and they turn the drum so the grains get tilted up to an angle. So if it was sand, you would expect it to just sit there at that angle as long as that angle is below the angle of repose. But these grains are small enough that they're getting kicked by the thermal fluctuations of the liquid that they're immersed in. And so what they observed is that the pile relaxes, okay? So this is creep-driven relaxation of a granular pile. And the creep is a thermal kind of creep. So the grains get kicked by the liquid, they tumble downhill, and what happens is that the slope angle diminishes through time. And so if you do this for very small particles that are very thermally activated, it relaxes quickly. And if you make the particles progressively bigger, you move across the Brownian to non-Brownian regime. And so eventually you make the particles big enough and they don't do anything, right? Morgan Houssaye with Jeff Morris did a granular analog to this. So they made a little Healy-Shaw cell, so a quasi 2D cell, but now it's filled with sand-sized particles, 400 microns. They tilted at a slope, just like this experiment. And then in order to mimic thermal agitation and see if it does something similar, they flowed a liquid up through here, right? So they flowed water up and created a pressure gradient, but below the fluidization threshold, and asked what happens. And what happens is it creeps and it has spatially localized rearrangements. And if you look at what happens over time, the slope angle relaxes as a power law function of time. And the rate at which it relaxes depends on how hard you drive it, right? But now you're driving it with a fluid instead of driving it thermally. These grains are too big to respond to the thermal kicks from the liquid, but they do respond when we apply a pressure gradient through them, right? So this is what led Nicole, my recently graduated PhD student, to ask the question, okay, so we have creep from thermal effects, we have creep from fluid effects, we have creep from shear. What about if I take a pile of sand and I remove all of that? We basically want the stripped down minimal system and say, does it still creep? And so this is the experiment. You take a pile of grains, you ready? This is PhD level stuff. You take a pile of grains, you pour it on the table, just step away. You just pour the sand, you let it sit there, and you step away, right? I mean, it's like watching paint dry, except slower and way more exciting if you know what to look for, right? So if you look at it with your eye, of course, nothing happens, right? If you want to know what the table is, it's a vibration isolating table, right? And so we try to minimize vibrations, but I'm in West Philly, the subway goes by a few blocks away, maybe that gets through. It's in a room where we try to keep the temperature and humidity constant, but they fluctuate a little bit. And summers in Philly get real humid, and so that does stuff. So you cannot do a zero disturbance experiment. But this is a minimal disturbance experiment, okay? If you look at it with your eye, it seems like nothing's going on. So what you need to do is look in a different way. And so if you want to spatially resolve motions in a pile that are very, very small, so you want to be able to know here and here and here and here what's going on. Of course, you could try to do this with a camera. You can measure very small displacements down to a micron optically if you zoom in like crazy, but then you're just looking at a tiny little piece of one surface of one sand grain. So if you want to look at all the sand grains, you can do a different technique, and the technique is diffusing wave spectroscopy. And I'm happy to give details about it later if you want, but in order not to bore people that are not interested, the basic premise is just you take a laser so that there's just a fixed wavelength, which is really only so we know what wavelength we're looking for, and we can eliminate all other wavelengths. We spread the laser out so that the spot becomes a blob, right? So now the laser is shining on this pile. And then what you do is, and by the way, you send it through a diffuser, so you randomize the photons. And then you sit there with a camera and you look at an angle. So you don't look at the reflected light, you only look at the backscattered light. So you are looking at photons that have taken a random walk through a structured medium. And so what you get back is a speckle path. You get speckles because the photons get concentrated in pockets, areas between grains and things like this, right? So you have a speckle pattern, which is somehow related to structure, but it's a non-unique inversion. So even though, so you can't actually know what the structure is. But the thing about these speckles is they jiggle. When the grains move, they change the geometry, they change the backscatter pattern, they change the speckles. So the speckles jiggle, and with that, you can measure strength. You can measure very small displacements. So, okay, so first, here's a real-time movie of the experiment, right? This is preparing a pile. All we're doing is pouring sand in a funnel. It relaxes to the angle of repose once we stop pouring it. And this is, the movie's still playing, right? This is what it looks like to you with your eye. It's like staring at a glacier, right? Like you look at it with your eye in real time and you can't see anything. It looks like nothing's happening, right? The movie's still playing. It's just a pile of sand sitting there, right? We all know what it does. Are you ready? Are you ready? This is what's going on when you look at it with DWS. All those blobs that you see are blobs of high strain rate, okay? So on the left, you're looking at a spatially resolved movie of instantaneous strain rate through time. And on the right, you're saying if we average all those pixels and plot the average strain rate, what does it look like? So in the beginning, right after the pile has frozen at its angle of repose, and it's like a loose, fluffy, freshly prepared pile, it's creeping. You see that the creep is distributed spatially throughout the pile, and that the creep is relatively fast. By that, I just mean dark colors, okay? So we're talking strain rates like 10 to the minus 5 per second. Sorry, the per second's missing, right? If you look at it after 11 days, it's still creeping. But you notice that the creep is slowed down. It's relatively lighter in color. And that the creep is starting to get localized to regions near the surface where the grains are under the lowest pressure. And then underneath, where the grains are under more confining pressure, that the creep is kind of getting preferentially slowed down or extinguished. Okay. So we have the spatially heterogeneous dynamics, and we have the slowing down of creep through time. So how does the creep slow down through time? It's a power law. So what do I know about power laws and creep? What does anyone else know about power laws and creep? There's this classic example in glasses where they call it Andrade creep, where you take a glass and you put a constant stress on it and you measure the response of the creep rate, and you see that the creep rate decays as a power law function of time. Here we're looking at a thing called the relaxation time. Sorry, I should have reversed it. The relaxation time is basically like the inverse of the creep rate. So a power law increasing relaxation time, the glass people like relaxation time. They don't like creep rate, they like relaxation time. But you know, flip it over, and this means a power law decrease in the creep rate through time, right? So there's these kind of phenomenological rules about why creep slows down as a power law, and this Andrade creep for glasses. The slope of the power law in glasses changes with different materials, but you always get a power law, and we get a power law. So we don't exactly know why, but the important point, first of all, is that the material is relaxing gradually through time under a constant stress, which in this case is the stress is its own, the self weight of the grains. And it's doing it like glass does. No one's ever seen that before. So there's something else, right? So then we can ask the question, all right, I pointed out to you that it was creeping faster at the top and slower at the bottom. What about if we want to take some window of time and average things horizontally so we can produce a vertical profile of creep, right? So things creep fastest at the surface and they creep slower with depth. So by the way, in the field, people do these things. They go to hillsides and they measure the creep rate and they measure depth profiles of creep rate. I kid you not, the way that they do it still, there's only about 4 or 5 studies in the world, is they go dig a trench, they put these pegs in a vertical stack, and then they fill it in, and then they come back 30 years later, right? So of course you could probably do this with tilt meters and things like this, but people put those on volcanoes. Nobody cares about spending the money and the time to put them in creeping soil. But in the 4 or 5 studies that we have around the world where people have done this, the creep rate is fastest at the surface and diminishes exponentially with depth below the surface. It's diminishing because the hydrostatic pressure is increasing, okay? So more pressure down here, slower flow. We put our data on top of there. We've normalized it all because they're exponentials. You can just divide them out. They all collapse, of course. This is not a smoking gun, but it basically says that in our lab little pile, undisturbed, relatively undisturbed granular pile, we have an exponential profile just like we see with field soils. The other thing, by the way, is that our creep rates of that sand pile sitting there in the lab are on the order of nanometers per second, which is on the order of centimeters to decimeters per year, which is actually pretty comparable to rates that soil creeps downhill, where people have bothered to try to figure that out, either by these pegs or by cosmogenic dating or whatever people do that date stuff that I don't really understand. It's not a diss about them. That's an indication that don't ask me about cosmogenic dating of soil because I don't know about it. So of course, I got this undisturbed, relatively undisturbed creeping sand pile, relaxing. I'm super excited about it. We're jumping up and down about it. To literally see something that you never imagined before is exciting. And then of course, very smart people need to come and rain on your parade and say, but yeah, but Doug, Nicole, out there in nature, creep is happening because the soil is disturbed, right? It's freezing and thawing and shrinking and swelling and animals are burrowing and trees are falling over and worms are digging holes and all that stuff. So you're going on and on about this creep happening in a pile that is not being disturbed. But I know that creep happens out in nature because soil is disturbed, right? Question that raises for us, if I wanted to recast that into something that would be a little more inspirational for me as a researcher, because saying, you didn't include anything relevant, so there's nothing to see here, it doesn't excite me. But if I did say, hey, if I take this pile now and I disturb it, is it functionally the same behavior, just maybe faster? Or does something qualitatively different happen, right? That to me is maybe a more interesting question. So what Nicole does then is add disturbance. And now I will admit that we're in the very beginning of this, okay? The parameter space you could explore is huge. And so we just started playing around with two disturbances that are pretty well studied in the granular world and in other worlds, right? And one of them is heating and one of them is tapping. So heating the pile, here we have like a hair dryer. We do it in a better way now. We use a Peltier plate. And turns out we have to do all kinds of things to make sure that the grains are being heated, but that the vessel that they're in is not changing its volume. So you have to have all these heat sinks attached to it and all this stuff. So I'm only going to show you qualitative data from here. The quantitative data, I would say, are in thesis form, but they're not yet in paper form, right? But what does the heating do? These are quartz grains, okay? These are glass particles. Their coefficient of thermal expansion is very small, but it's not zero. And in fact, we can measure it. This DWS technique is so sensitive. One of the ways that you check that you're measuring strain properly is you take a material with a known thermal expansion coefficient and you heat it and you measure the strain with the DWS and you see whether you get what you're supposed to get, which we did, right? So we heat these grains, and when you heat them, what's interesting is that it rejuvenates creep. What do I mean by rejuvenate? So take a pile, let it sit there for a couple days. So it's creeping slower and slower and slower. And so it's getting older, right? Our poor pile is aging. It's getting shorter and slower as it goes along. And then we come along with this fountain of youth. We just put a heat gun or a Peltier plate on it. And what you do is you reverse 2 days of aging with 30 seconds of heating. So you warm it up to like 50 C from ambient, which is whatever it is, roughly 20 C. You heat it up to 50 C. And what happens is the creep rates shoot up. Now, I can't tell you exactly, we're experimentalists here, okay? So for sure, the grains are expanding, but the response rate to heat is pretty fast. So maybe it's changing the humidity level at the grain scale. Maybe it's changing some chemical bonding stuff. I can't tell you what's happening. These are all the questions my tribology homies got from me. I can't answer them, but I can tell you that you can apply a few seconds of heat and you can reverse days of aging, okay? How about if you tap it? So tapping for us is relevant to shaking, right? So, and our tapping, really, it's a metronome that's hitting the side. And so really what it's doing is shaking globally the whole system. So if you shake it or tap it, so you do age the system, you age it faster than if it just sits there on its own, right? So if you shake it, the strain rate, the creep rate drops much quicker. Essentially, the pile gets stiffer and stiffer. But it's not homogeneous everywhere. So if you tap it, the creep rate overall, the average creep rate slows down quickly. However, what also happens is it phase separates. So an initially loose pile is creeping everywhere. And we already know, even in the other pile, that after some aging, it's creeping more at the surface than it is down at depth, but that change is continuous, right? It's our exponential thing. But if we tap it, what happens is it forms a yield surface. So there's a core, which is getting more and more compacted and creating granular arrangements and other things that make it slow down. But then the surface, because it's not under a lot of confining pressure, gets excited. And so we take an initially loose pile with a continuous decrease in creep rate, and by tapping it, we cause a phase separation where it creates a flowing layer that keeps flowing every time we tap it, and a core that just gets stronger and stronger and stronger and stronger, right? And so obviously this is an idealized little experiment, but you can immediately start thinking about what's happening to the granular earth as it's getting shaken, right? Subcritical shaking is basically always going to age the material and make it harder. But it could also cause yielding at the surface, right? So you can have these two contradictory things where you shake the granular earth and you landslide on the surface, but you strengthen underneath. And you can even create internally, right, these failure planes. So as a side note, we're heating and cooling and heating and cooling. There should be an elastic component, right? And indeed, so here the direct thing that we measure is it's kind of nuanced, but the direct thing that we measure is this correlation function, right? We have these speckles and they jiggle, and that causes the correlations in the image to diminish through time. If the motions that the grains undergo are irreversible, the correlation function goes down monotonic. If there's something that is reversible, hence elastic, you could reverse it in the correlation, right? That you could have the speckles change their structure, but if you reverse it, they can return to the structure that they had, right? And so right here, we're looking at a movie of a pile that is repeatedly heated and cooled, heated and cooled. And you see there's an overall decay, which is the irreversible or plastic component of creep. But there's also this reversible component, right? Which is the elastic component. It turns out, you know, if you go to the field and you measure like thermally driven creep, like in this case, looking at thermally driven creeping rock falls on the side of this glacier, you have cycling temperature and other things like this. And what you see is an overall net displacement downslope, but also a reversible component. So we think that what we're seeing in the lab is relevant to these field settings. By the way, everything I've presented to you so far, we're using spherical glass beads, not because we're trying to make any tricks, but because in order to take the correlation function and turn it into strain, we need to know the optical properties of the material precisely. You can still do this technique on other materials that are opaque or have optical properties that you don't understand, but you become unmoored from the optical theory, which means that you can do this and you can look at relative differences in creep within the pile, but you cannot turn that into strain, okay? So you can chuck in whatever material that you want, you can watch it, and I mean, creep is going to creep, right? I mean, all these materials are going to creep. That's what they do. But you will notice interesting differences in them, right? Perhaps most interesting to us is, where is it? Flour. So the flour turns out to develop these internal slip planes. I have movies of this that are beautiful, where basically when you pour the flour, it's clumpy, so it kind of builds up in clumps and collapses quickly and makes these internal shear surfaces. But once the pile's done being built and it's sitting there, all of the slip planes that develop during pouring stay there as perennially active regions of creep. So the inherited structure from pouring is preserved and becomes a dynamical structure in terms of that you have enhanced creep there, right? So you can start letting your imagination run wild in the ways in which the internal structures of granular materials on the earth are influencing how creep is localized. By the way, I'm not going to get into this now because I want to get to the other part before I finish, but creep also happens in simulations. So we have all these things we can't control in our experiments, right? And we have the chemical bonding and all this other stuff that people are worried about and that for sure happens. But in a discrete element method simulation, you can just put in exactly what you want, right? And Beirut and Carlos did this work a couple of years ago. And basically, I'm not going to get into the DEM stuff, but it's a well-established method. And if you're curious, we use the Hertzian Midland contact condition, right? And so basically, you try to solve F equals MA, you have to deal with the tangential slip. So you have to build in some component of how you treat the friction as a function of the slip locally. You can play around with the rules. The quantitative results change, but the qualitative results do not. If you make a pile of grains in a DEM simulation and you make it below their angle of repose, you get spatially localized rearrangements and you get creep and you get an exponential profile. And if you tilt the thing above the angle of repose, you get a flowing layer separated from a creeping layer underneath, right? I'm not going to make any quantitative comparison. It's just to make the point that creep is not an artifact of our experiment somehow. And it also indicates that it has more to do with granular structure and friction than a lot of those other factors if we can also make it in the simulations. So the sand pile that we prepared was as close to critical as possible, right? We poured it to the critical angle and we let it go. A lot of landscapes organize themselves to be at or near the critical condition, that razor sharp line between failure, right? That delineates failure. This is an example of what near critical transport looks like in a river. This is the bottom of the Sacramento River. So there's a turbulent flow moving over these particles. This is pebbles, they're heavy. Every once in a while, they get kicked by a turbulent burst or they get knocked by another pebble, their neighbor, and they move, right? And so that's just to give you, that's what near critical transport looks like. But here's the thing is, rivers organized to be near critical for a pretty simple reason. It's basically that imagine I have a flow that is so big that transport gets activated along the base of the river and also on the walls. So as these pebbles on the walls get picked up or entrained by the flow and move downstream, they also move into this potential well. They move down into the center of the channel. And there's no mechanism to take a heavy pebble and push it back up, which then means that if you have a fluid stress that's high enough that you activate transport on the walls of the channel will widen, which will diminish the flow depth, which will diminish the stress, and which will bring the system back to near the critical point, right? So rivers organize so that their stress that they organize to during a flood is a small factor larger than the critical stress. And we typically define this with a dimensionless shear stress, which is the fluid shear stress normalized by the submerged pressure of a particle, right? So when the fluid is winning over the submerged weight of the particles move. This is really is a friction coefficient, right? We're just neglecting the actual friction itself, right? But it's just the ratio of a shear stress to a normal stress. So you can ask the question, do rivers creep? And if they do creep, what does creep do in a river? There's a lot of vexing phenomena observed in rivers. So first of all, there are these experiments that are done out in the field in natural rivers where they use geophones or seismometers or other things to detect when a flood comes and the river level starts rising, when do the pebbles in the stream start to move? And you can define that as the critical stress, right? And what you observe is that if you measure that critical fluid stress, how high the flow needs to get before the particles suddenly start moving or getting eroded. If you look at it as a function of time, so you look many floods, what you see is that the fluid shear stress goes through these cycles where in one flood, it starts in this case at 100 pascals, and the next flood is higher and higher and higher. So each subsequent flood needs more stress than the last flood in order to make transport happen. But at some point, it gets reset and then starts climbing again, and then gets reset and starts climbing again. And so there's flows that seem to be hardening the bed, making it more rigid and or more resistant to deformation. And then occasionally it gets whacked and it gets reset. Subcritical flows cause grain rearrangements in a flume. So if you want to have an idea what's going on and it's hard to monitor these grains in the lab, you can go, or in the field, you can go to the lab and you can take a bed and run a flow over it, but run a flow that is not so high that the grains move in bed load. So you run a flow that's boring. It's like our sand pile. You prepare a riverbed in the lab and you run water over it, but you don't run water over to the point that it causes erosion. And you just run that low flow. And what you observe is if you continuously run that low flow, the bed somehow hardens. The bed somehow becomes harder to erode just by running a subcritical flow. You know I'm going to invoke creep, right? And then this experiment done by my colleagues, they showed that subcritical flows actually compact the bed by creep, right? So if you run a flow that isn't big enough to directly pick up the particles by lift and drag force and move them along, you're still driving the grains with a stress. And it causes creep to happen. And so in this particular case, what they examined was creep due to compaction. So as you're shearing it, the bed is compacting, so the volume fraction is increasing. And as the volume fraction increases, the critical stress that they needed to bring up to cause the bed to crack and start eroding, it increased monotonically with the volume fraction, right? So if you increase the volume fraction, then you increase the stress. And in this case, that volume fraction was increased by creep. The volume fraction is not the only thing going on. So we wanted to examine glassy dynamics in a riverbed. And I do big flumes, all right? I do have some big flumes, but this is a tiny flume. This is a flume that's about this big. We really wanted to focus on the granular part. So these are beads, they're spheres. They're bimodal so that we avoid getting crystallization. Well, they're not they're slightly bimodal, right? So they're grains that have two sizes that are only different by about 10%. These are beads in oil. It's a laminar flow, no turbulence, no anything like that. But what we do is we make the particles refractive index match. So they're transparent beads that have the same refractive index as the liquid that they're immersed in. So if you shine a light through it, when the light passes from the liquid to the solid, it doesn't bend, right? And so now if you put fluorescing dye in the liquid, when you shine a laser through it, you get nothing lighting up where there are particles and you get it lighting up where there's liquid. So now you can do tomography cheaply, right? You have a 3D granular bed, but you can just illuminate a cross section with a laser and you can watch what happens in that cross section, even though there's other grains between the camera and the plane, right? So we do this so that we can look at the internal deformation of the bed away from the wall of the vessel. And here it is sped up. You notice this is in minutes. Flows from right to left. So the lid spins and it pushes a liquid. The liquid pushes the particles on the surface, but those particles that move on the surface drag particles under them. And you notice first that it looks kind of like at this frame rate. Yeah, maybe there's a layer right here where above it, the bed is fluidized and below it, nothing's happening. But if you start looking, pick your favorite grain and just follow it, you will see that the grains are moving even below the bed, but that they're moving slowly. They're creeping, right? So creep is happening beneath this flowing layer. And what we discovered recently, so David was an amazing PhD student from Unicamp in Brazil that was visiting my lab for 6 months and managed to write a paper from that. And it's basically that creep hardens the bed, right? And so we were interested in what was going on there. And so the basic idea is that what we did was we took this granular bed and we subjected it to pulses of constant fluid stress. So you turn on the flow at a constant rate and you drive it at that fixed stress and then you turn it off and then you turn it on again. And the only reason we turned it off and on was so that we could basically take these 10-minute windows where the flow was on and average the hell out of it. So we could compare one 10-minute window to the next 10-minute window to the next one to the next one, right? And so this is a profile averaged horizontally. So this is a vertical profile of the particle velocity. This is the particle concentration, which is high in the bed and diminishes here. And this is the strain rate. Let's just focus on the velocity. At the first stress cycle, the velocity diminishes into the bed, but it does so continuously. At the second stress cycle, what do you see? Phase separation, the same thing we saw in the tapped granular pile. Now you see this kink in the profile. You're starting to develop a very well-defined fluidized region and a region underneath that's not doing much of anything. Here we are, if you want to look at this in terms of velocity. So now we're looking at the velocity of particles where the heat corresponds to the speed of the particles as a function of depth. So you turn the stress on, you see that the particles on the surface move fast, and you see quickly it activates down to depth. The next 10-minute cycle, there's much less activity. The next 10-minute cycle and every subsequent cycle, you see that the particle activity goes down. Now, if all of this was due to compaction, if you reverse the flow direction, not much should happen, right? If we reverse the flow direction, after reversing the flow direction, the particle activity should look much the same as before. And the going idea was that this is all of this creep-driven slowdown, or all the slowdown and creep was because of compaction. But here, we can reverse the direction, and when we reverse the direction, we find a lot of motion. We basically find that we've reactivated, transported the bed, which is telling us that volume fraction is important, but that also that there's a fabric that's developing to resist the direction of strain that is not associated with volume fraction change. Another way to put it is, I can have different granular materials with the exact same volume fraction, and their level of mechanical stiffness or strength can be very different, right? There, I said it. Okay, so I'm finishing here. A few things for us to ponder. So first of all, there are these glassy models. There are phenomenological models that are used to describe experiments and simulations for true molecular glasses, where the creep is driven by thermal agitation. And we are wondering if we can have a kind of activated creep, but where mechanical noise instead of thermal noise is the thing activating creep, and whether or not we can extend the model, the glassy models for flow or rheology of creeping systems to non-thermal systems where mechanical noise plays a role akin to thermal noise. Some theorists have suggested that. We don't know how to do it. Another thing I want to bring up is what's the role of material properties like size of particles, friction, cohesion on the scales of these problems and on the dynamics. And so there's a little part that I didn't show you, but it's fine because it comes up here in the concluding slide, that I had all these little hot spots, right? So in our material, we have these hot spots where creep was occurring. And I told you that these things are basically behaving like little fluidized regions. Well, basically, once this hot spot relaxes, rearranges, the stress gets distributed to the surrounding medium, and there's an elastic deformation. And so it turns out if you take the correlation function of all of the strain maps that I was showing you, and you average the hell out of it, you get this quadrupolar correlation function to the strain field, which is basically the signature of elastic redistribution, elastic deformation from a redistribution of stress around a locally yielded point. If you're familiar with Eshelby inclusions and that whole idea, right? This is your Eshelby inclusion. And so there's this mesoscopic scale that emerges in the system that is characteristic of elastic deformation due to the redistribution of stress surrounding a localized fluidization. Right? That's the pattern you see in earthquakes, right? So you get fault slip, you get elastic redistribution of the stress, and you get a strain field that looks like this, right? But the scale is gigantic. I'm not saying that we've now discovered something that's going to help us understand earthquakes, but what I want to say is there's something rather generic that says localized slip is localized failure and localized fluidization, that they all have the signature that you get a little bit of failure and then the stress gets redistributed and you get a big elastic deformation field around it. So I want to know why these little pluses are this big in my experiment and why they're this big in an earthquake, right? Of course, it also leads us to ponder which events harden and soften granular landscapes, right? In our experiments, we have some ideas of what did it in our experiments, but there could be others. And the last point, this is something that my former student Nicole has talked about is, we think about earth flows, the slow moving landslides, but instead of creeping distributed in a bulk like my sand pile, they have slip localized along a surface, right? It's kind of more like a fault, like these slow moving earth flows are sliding along at a contact line, and then occasionally they fluidize and they go, right? And so one of the things that we're wondering about with these earth flows is whether what we're looking at is creep along a shear band, that any pile of granular stuff, if you shake it, is going to phase separate and create a fluidizing regime at the surface, right? And then instead of the creep being distributed in these little popcorns, it's going to happen localized along a surface, right? And so this is another connection we're interested in making. Thanks for your attention.
Okay, time for questions. We would first like to invite the students to ask questions.
Now, there was a question about the heating.
Yeah.
Do you think that it could be because the effective pressure goes down because the gas within the pore space increase?
So I don't think so, only because the material is so permeable. So, the grains are like 0.5 millimeter. And of course, air is not very viscous, so the permeability is really high. So the question, right, was about, Jardel's question was, if you're heating this stuff, right, you could have a change in the effective stress, essentially the confining pressure, because you're like heating a gas that now, right, could expand. And if this thing were a sealed system, then that could happen. But I think that, we've been asked this once before, and we did the calculation, but basically the permeability is through the roof. And so we're pretty certain that basically the gas expansion just drives it to leave, and that the effective pressure within the pile is probably not changing at all. Yeah, but it's a good question.
Is this the permeability of the entire system, or there's no local regions of variations of permeability?
I mean, I'm sure there's local variation in permeability, but even there, it's going to be exceptionally high for, if you're worried about such an effect. Because even when they're tight, the difference between the loosest pack and the closest pack is about 8% in volume. But these are spheres that are, 0.5 millimeter. So you never really end up with permeabilities that get anywhere threatening in the regime. Where we'd be worried about that.
I have a question.
Yeah.
It was related to the size of the beads that you used.
Yeah.
You said you used them around 10, they're around 10% size difference.
Yeah.
Is it possible that you're able to, is it possible that you'd be able to have a wider difference in the sizes? Basically in an effort to see what how the slip planes would develop.
Right.
When you have such a bimodal distribution, because in the earth it's not all
Right.
realized in one size.
Right.
Many places
Yeah.
that have
Yeah.
place and sands.
Mm-hmm.
So I was wondering if that's something you guys considered.
Yeah. So first, I'll give you a quick reason why we do this, right? So it's pretty typical in the granular world. So we want the material to be disordered. We don't want it to crystallize. So if you have uniform particles, uniform in size in their spheres, if you shear it, what will ultimately happen is, even if the particles start out in some kind of disordered configuration, what you will observe after some time is that the particles do this, right? So they start to align in layers. And then you have layers that slip past layers entirely because they've organized in a crystalline structure like this. And that's not a disordered system. On the other hand, if you do an experiment with particles that are bimodal or polydispersed with a wide range, and the size range is quite different, what will happen after some time is that it will segregate by size. This is a Brazil nut effect, like you shake the mixed nuts, and if a big grain happens to kick up and a small grain goes underneath it, there's a ratcheting effect. If you're a continuum person, you would also say when this is shear, there's a velocity profile. And because it's exponential, you can look at the velocity profile across the grain and see. And so, on the one hand, do it all with one size, you get crystallization. On the other hand, make them too polydispersed and you'll have segregation, but that takes time, which now means you have a time varying thing going on while you're trying to look at the other stuff. So for now, the trick that people do is you pick a bimodal mixture or a polydispersed mixture, but with a limited range in size. And so if the grains are slightly different in size, they won't crystallize, but they also won't segregate because they're not different enough. And so this is the reason why people in these experiments will typically do it, is you want to frustrate these other effects. But now that we have these results, and we have isolated it from those things, we can intentionally introduce those things if we want to. But then we're also going to have to track the segregation that's happening here and all that stuff, which will be hard. Yeah.
Sorry, I think that's your explanation for why most of the your son is German.
I'm only laughing not because of you, but because I didn't tell you. And this is the question. This is the question, right? So, you know, what we're trying to say here, right? So, most people thinking about creep out there, when we say that disturbance drives creep, I think the picture has literally been that grains out in nature get mechanically pushed by these disturbances, right? So freeze thaw or like a gopher or whatever is physically pushing grains, right? And the one thing that we can tell you now from the experiments, but especially because we did simulations also, is that you don't need that. So I'm not going to give you, so if you're asking what's driving creep, I don't have an answer, but I would flip it around and say, what is preventing it? So what I mean is that if we think of a pile of grains as some more Coulomb condition, where we say, look, here's this thing, and it's a solid, and it's going to be a solid until I push it hard enough that it breaks, and then it's going to do a thing. Then creep is like paradoxical. I call creep like the shady, the seedy underbelly of static friction, because beneath a given friction value, our whole worldview says nothing happens. Right? What I turn around and say is that in a disordered material, there are infinite number of states or configurations of particles that have the same stability or same energy, right? In a crystalline material, the grains will organize into some minimum energy state, and there's one configuration. In a disordered material, on the one hand, I can have an infinite number of arrangements of particles, be they grains or atoms, that have the same stability. Think about that though, the other side of that coin is in infinitesimal perturbation to any one particle, right? Because the particles happen to come to rest in some metastable state, that if I just were to pick one random particle and move it a little bit, I change the stress balance on that particle, which changes the stress balance on all the other particles through those force chains. And so what happens then is that it says that when I have a disordered material, it is always metastable and susceptible to infinitesimal perturbations, right? Anything that disturbs one particle the tiniest bit disturbs the stress state in a huge region. And so you now change the stress balance on any grain in there, right? And so in our experiments, it could be anything. In the simulations, though, it's deep, right? Because in the simulations, we don't have humidity or temperature or anything else. What we have is a rounding error at the 32nd decimal place. So everyone wants to invoke some kind of disturbance, including me, because it's so paradoxical about what's going on. And in the simulations, you have boundaries. The fact that the system is not infinitely big, but there's boundaries. So maybe the boundaries themselves are some kind of disturbance to the grains. And you also have the fact that you solve the equations of motion, but like, you know, you round them at like the 32nd decimal place, which is like an infinitesimal perturbation that's happening all the time. And that's kind of the best answer that I can give you, if that makes sense.
So why does it happen mostly near the surface, not near the
Oh, I see.
fine pressure?
Yeah, exactly. Sorry. Yeah, the reason why it's happening at the surface and it diminishes with depth is, yeah, it's just the confining. Yeah, exactly. So the hydrostatic burden goes up as you go down deep. Yeah.
But you're not saying that you're violating the second law of friction as far as the normal force versus the friction and the shear traction, but that there is inherent to the entanglement of the particles or some friction related to that these infinitesimal disturbances potentially are then causing this two frictions to go against each other, both at the microscale and the scale related to entanglement of particles.
So,
And
sorry, go ahead.
because you
Yeah.
friction.
So let me phrase it this way. Okay. I didn't present the rheology side of this story, but we've done rheology in the creeping stuff. Basically, you know, if you say that, imagine I'm interested in friction on a grain. And if I calculate friction on a grain as being a local quantity, that I can say it's the local shear stress divided by the local normal stress, okay? And if I do that for a granular system and I lower the shear rate, what you expect is that the friction goes down to a static value. It converges in the limit of vanishing shear to a constant value, which is static friction, right? Can you imagine it, right? So like this, if we have, right, so this is friction and this is shear rate or some appropriately dimensionalized shear rate. And this is US, right? And so you expect that as you go down, you do this, right? If, though, you measure friction and you define it in this local way, and you keep driving the shear rate down, and you measure it, what actually happens, this. The local friction appears to go to 0 in the limit of vanishing shear rate. The answer lies in the fact that the stress defined locally does not work when you are in the creep regime. That you have to introduce a non-local scale. So the way that people have rescued this problem so that it doesn't contradict the idea that we can converge toward a static friction, it says that I have to introduce, if you're familiar with turbulent flows, like we have to introduce a Prandtl mixing length or some, you know, when flows get turbulent, the mixing isn't happening molecule by molecule. You need to now declare that there's a scale that's big that mixes grains. The non-local rheology models is the same thing conceptually, except it's not in the high shear limit, it's in the low shear rate limit. And they have to introduce a non-local length scale and say there's something going on where now the mixing length of grains is big. And if you introduce that into the model, you can pull this up to here.
And that's how you found force input.
However, no one has found a non-local length scale that matches what you need in the phenomenological rheology model. So the rheology models work beautifully to describe this situation, but they have this length scale they need to put at them. And when you go looking, you don't find it. So that's kind of an open question. If you're a practitioner, you might not care. But if you're wondering like what's going on with what we're really challenged about with friction here, there's a story there, and like a story that has yet to unfold.
So due to the time limit, we have last question from the Zoom. Casper Pranger is asking, I was wondering if you have used your methods to closely investigate the temporal transition from creep to effective yielding in a granular medium. I guess the riverbed experiments show a special transition. And if so, what's your view on the nature of this temporal transition?
Okay, so that everyone doesn't stay around forever, and I'll tell you, what was the name? Who's the person asking? Casper. So, and Casper, you should feel free to email me and follow up, because I don't want to give a lengthy answer now. Short answer is absolutely. We have been investigating the nature of the yield transition. Oh, yes, sorry. Absolutely, we've been investigating the nature of the yield transition in a lot of different materials, and it's a second order phase transition, so it's continuous. All the quantities diverge, but they diverge continuously around the critical point. And if that means something to you, great. If it doesn't, just reach out to me, because we have lots of stuff, but I'm not going to get into it all right now. Yeah.
Will do. Thank you.
Cool.
Okay, let's thank